Hello, so this video will cover atomic orbitals and also quantum numbers. So we met last time when we looked at atomic absorption and atomic emission spectra, that an emission spectrum gives you a series of lines, and these lines correspond to energy differences between the levels within an atom. When an electron falls back down, it emits the radiation. So each line of the emission spectrum represents radiation of a specific wavelength, which we know is related to frequency. And then from that, you can calculate the difference in energy levels from the wavelength of the radiation of light. Now, hydrogen only has one electron, but the emission spectrum of hydrogen has many lines, and this is because this electron can transition between the many different energy levels in the atom. Remember, we looked at the second video of the last lesson. So here are a series of the lines that are shown in a hydrogen emission spectrum. So here, where we've got the Lyman series, you can see what this is all the transitions that end up with the electron at energy level 1. The Balmer series is a series of lines where the electron falls back to energy level 2, and the Paschen series where it falls back to energy level 3. This is why there's more than, even though there's only one electron, there's more than one line in an emission spectrum. It's all the possible combinations of electron transitions between the energy levels in an atom. Now you get specific lines, remember, because each energy level has a specific energy. And this can be explained if electrons, which like photons, display the properties of both particles and waves. Now we say that electrons behave as standing or stationary waves in an atom. These are waves that vibrate in time but do not move in space. There are different sizes and shapes of standing waves that are possible around a nucleus, and these are known as orbitals. The simplest orbital is spherical, but you get more complex orbital shapes as well. It doesn't matter how complex or simple the orbital, it can only ever hold a maximum of 2 electrons. That's a really key point to remember. Each orbital can only hold a maximum of 2 electrons. Now, electrons within atoms have fixed amounts of energy called quanta. Okay, it's not a continuous variable, they are fixed quantity of energy. And this means that we can use quantum numbers to describe electrons. There are 4 quantum numbers that you need to know in chemistry. The first one you've actually met before, but it's never been called a quantum number. The principal quantum number is given the symbol small n, and it describes the main energy level for an electron, and it's related to the size of the orbital. So for example, way back in National 5, perhaps even in 3rd year, when you were doing electron arrangements, and say you had the electron arrangement for lithium. The electron arrangement for lithium is 2, 1. There are 2 electrons in the first energy level, and there is 1 electron in the second energy level. That first energy level has a principal quantum number n equal to 1. That second energy level has a principal quantum number n equals to 2. Okay, so it just describes basically the energy level or the shell where those electrons are found. The next quantum number is called the angular momentum quantum number, and it's given the symbol small l. This quantum number determines the shape of the subshell. Within each energy level or shell, there are subshells. The shape of these subshells is determined by the angular momentum quantum number, and it's given a value from 0 up to n minus 1. So it's never equal to the principal quantum number, it's always 1 less than the quantum number, from 0 to 1 less than the quantum number. The next one is the magnetic quantum number, and the symbol for this is M with a subscript L. If you go back to some advanced higher books, even a couple of years ago, this will be different, okay, because they have changed the symbol. The SQA have changed the symbol for magnetic quantum number, but you will see it as a small m with a L as a subscript. This one determines the orientation of the orbital, okay? Some orbitals are spherical, they don't really have an orientation, but there are others that have different shapes and they will align themselves along or between different axes. We'll look at that in a bit more detail later on. The value of the magnetic quantum number can be anywhere between -L and +L. So minus the value of the angular momentum quantum number to all the way to plus the value of the angular momentum quantum number. The final quantum number is a spin magnetic quantum number, M subscript S. It determines the direction of spin of an electron within an orbital, and it can only have two values, either +0.5 or -0.5. Now, electrons are arranged in shells. The shell that's nearest the nucleus is the first shell, and any electron in this first shell has a principal quantum number n equals 1. So as we saw with lithium, the first two electrons in the first energy level will both have a principal quantum number n equals 1. So the first shell has a principal quantum number n equal to 1. Any electrons in the second shell will have n equal to 2. The higher the value of n, the further the electrons are from the nucleus. If you got to potassium, for example, which is 2881, that one electron, the one outer electron, has a principal quantum number of n equal to 4 because it's in the fourth energy level. These electron shells, okay, these energy levels are divided into subshells, and these are described by 4 letters, S, P, D, and F, and they've all got different energies. S has the lowest energy, followed by P, followed by D, followed by F. You need to be aware of the F subshell, but we don't do very much on it at all in advanced higher chemistry. We concentrate mainly on the S, P, and D subshells. So we're only dealing with elements up to 36. Okay, so in the first shell, so this is principal quantum number n equals 1, there is one subshell called the 1s. This one shows that it's within the first subshell. Within the first shell, sorry. In energy level 2, so shell 2, there are two subshells, the 2s subshell and the 2p subshell. Remember that the angular momentum quantum number can have a value from 0 to n-1. Okay, so if you have 1 as your principal quantum number, you can only have one subshell because L will be equal to 0. If you have 2 as your principal quantum number, you can have two subshells. The 2s has an angular momentum quantum number of 0, and the 2p has an angular momentum quantum number equal to 1. In the third shell, there are 3 subshells. Okay, the 3s has a value of L equal to 0. The 3p has a value of L equal to 1. And the 3d has a value of L equal to 2. In the fourth subshell, it's exactly the same. Okay, this time we've got an additional subshell of the 4f, but like I say, we're not going to do very much with the f subshell at all. Now, each subshell contains one or more orbitals. So we start off with shells, break it down into subshells, and then each subshell contains one or more orbital. And these orbitals are defined by the angular momentum quantum number L. It relates to the shape of the subshell, and as we've said, it can have a value of 0 to n-1. this table summarizes the principal quantum number and the angular momentum quantum number for each of the subshells. Remember that L can have a value from 0 to n-1. Let's have a look at the actual orbitals themselves. So an s orbital is spherical. The 1s orbital is the one closest to the nucleus, and it's smaller than the 2s orbital, which is further out, and which again is smaller than the 3s orbital. The first shell has only 2 electrons, so it has only one orbital, as we've seen here. The 1s orbital is the only orbital in the first shell. In the second and later on shells, they have p orbitals in addition to an s orbital. The p subshell has 3 different orbitals, and they have the same energy. And this is a very commonly asked question. Okay, orbitals that have the same energy are said to be degenerate. Either they ask you, what does degenerate mean? Or they'll ask you, what's the term used to describe orbitals that have the same energy? So there are 3 p orbitals. This is the kind of dumbbell shape that they have. And their only difference between these, because they all have the same energy, is their orientation in space. So if you have a look, the px orbital lies along the x-axis, the py orbital lies along the y-axis, and the pz orbital lies along the z-axis. Each of these orbitals can hold 2 electrons. So in total, the p subshell, which consists of the px, the py, and the pz orbitals, can hold 6 electrons. So the key points there, the shape of the p orbital, you can be asked to draw the shape of a p orbital. And then, like I said, the only difference between them is they lie along perpendicular axes. Everything else is the same. So the second shell, this is the second energy level, can hold a maximum of 8 electrons. You'll remember that from electron arrangements that you've done in 3rd and 4th year. Those 8 electrons are broken down into 2 electrons in the 2s orbital and 6 electrons in the 3 2p orbitals. Okay, so that's where we get the 8 electrons from. If we have a look at the magnetic quantum number, it describes the orientation in space of the orbital. Okay, it's got any value between -L and +L. So for example, so this is our energy level 1. Our value of L is 0, which tells us that it's the S subshell. And because it's from -L to +L, our value of the magnetic quantum number is also 0. So this is the 1s orbital. For n equal to 2, so we're in the second shell now, for our 2s orbital, L will equal 0, telling us it's the s subshell. And ml will also equal 0, because a s orbital is spherical. For our 2p orbitals, the value of L is 1, and then we have 3 values of a magnetic quantum number. 1 represents the px, 1 represents the py, and 1 represents the pz. You will not be asked to attach a specific quantum number to a specific p orbital, but you can be asked to give the quantum numbers for an electron in a p orbital, and in which case you can use any of these for 3 values. When you in the 3rd energy level, we have 3s, which again follows the same quantum numbers. The 0 represents the s subshell, and the 0 again for the orientation in space. This 1 represents this time the 3p subshell, and again there are 3 values to represent the 3px, the 3py, and the 3pz orbitals. When L equals 2, now we're into the d subshell. Because it has a value of minus L to plus L, there are 5 d orbitals. And this is where, if you looked in your data book, you may have noticed, perhaps last year, that some of the electron arrangements say that the atoms have 18 electrons in the third shell. So 2 of these electrons are in the s orbital, 6 of them are in the 3p orbitals, and then there are 10 electrons which are in the d orbitals. So each of these 5 d orbitals holds 2 electrons each. Okay, there's the shapes of the d orbitals. I haven't seen a question where you've been asked to draw the shape of a d orbital, but you have been asked to identify them and to actually name the specific ones more recently. Again, like the p orbitals, they are degenerate, which means that they have the same energy as each other, but they have higher energies than the s and the p orbitals. The dxy, the dyz, and the dxz all have similar shapes, and if you look at the lobes of the dumbbell, they lie between the axes. So the dxz, the lobes lie between the x and the z axes. For the dyz, the lobes lie between the y and the z. And for the xy, the lobes lie between the x and the y axes. The dx squared minus y squared orbital, the lobes lie along the x and the y axes. And the dz squared, which is actually the most commonly asked about one because it's got a unique shape, lies along the z-axis, and then it has this kind of donut shape around the center. So you should pause this video here and watch the electron orbitals video. If we have a look at the spin magnetic quantum number, again, in older books, you may see that this is written just as an S rather than the MS. It's changed recently. Well, it hasn't changed recently. The SQA have changed recently what symbol they're going to use for it. And this determines the direction of spin of each electron in the orbital. The electrons can spin clockwise, and to show this, we use an arrow pointing up the way. Or they can spin anti-clockwise, and this is represented by an arrow pointing down the way. Now, the Pauli exclusion principle states that no 2 electrons in any one atom can have the same set of 4 quantum numbers. That's important, and it's a commonly asked multiple choice question as well. This means that, as we've met already, the maximum number of electrons in any orbital is 2. Because this last quantum number, the spin magnetic quantum number, only has 2 values, +0.5 or -0.5. And if there are 2 electrons in an orbital, then they have to have opposite spins. So one of them must have a spin of +0.5, the other one must have a spin of -0.5. So we're going to complete the table to show the quantum numbers for all 10 electrons in a neon atom. So we're going to build it up step by step. So we've got the first electron. It's in the first energy level, okay, because our electron arrangement of neon is 2,8. Okay, so this is in the first energy level. It will be in the S subshell, and therefore if L equals 0, then ML must also equal 0. And for this electron, it's got a spin of +0.5. For our second electron, again, it's still in the first energy level. It's still in the S subshell, and therefore if L equals 0, then ML must also equal 0. And this time, because no 2 electrons can have the same 4 quantum numbers, this one must have a spin of -0.5. You can fill this out in your booklet at the same time. So now, those are our 2 electrons that are in the first energy level. We're now into the second energy level. So we've got 2, and then we're going to put them into the S subshell first of all. If L equals 0, then ML also equals 0. And we're going to give this electron, we'll just follow the pattern, a spin of +0.5. Our next electron is also in the 2s orbital. So S is given a value of 0. And then if L is 0, ML is 0. And because no two electrons can have the same 4 quantum numbers, this one must have a spin of -0.5. So these 2 electrons, 1 and 2, are in the 1s orbital. 3 and 4 are in the 2s orbital. Now we're into the 2p orbitals, okay? So again, we're in energy level 2. We're now in the p subshell. So our value of L is 1. Our value of the magnetic quantum number can be from -L to +L. So we'll just start with -1. And our spin, +0.5. 6 electron is also going to be in the same orbital. So we'll have the same of the first 3 quantum numbers, but we'll have an opposite spin quantum number. So say, for example, that -1 represented the px orbital. As I said, you're not going to be asked to do anything specific as that. Then these 2 electrons would be in the px orbital. We can't put any more into that orbital, so we're now into the next one. Okay, so we're in energy level 2 still. Our angular momentum quantum number is still 1 because we're still in the 2p subshell. Our magnetic quantum number needs to change. Okay, so it's now 0. So this could be the 2py orbital. And then our spin quantum number, +0.5. Repeat the same for the next electron, but this time an opposite spin. And then finally, so we filled the px, we filled the py, we're now going to fill the pz. So our value of this one for ml, because we've got -L to +L, will be +1. And then our spin, +0.5. And then exactly the same, but a opposite spin. Okay, you should now be able to answer questions 15 to 18 in the questions section. Again, post your work so that we can have an idea of how you're getting on. It also can count to evidence depending on what happens with exams next year. There'll also be a short check test on this as well. If you have any questions, please ask.